So in this section, we're talking about electron configurations and periodic properties. So we're going to learn some different properties like atomic and ionic radii, ionization energy, electron affinity, and electronegativity. And then what we're going to do is we're going to look at the trends of each of those properties and how they relate to the periodic table. So the first property we want to talk about is atomic radii. And because the boundaries of an atom are fuzzy, they're cloudy, we can't actually measure from left to right. You know, if we were going to measure the radius of a sphere, normally we could just measure that diameter from the left outer edge to the right outer edge, but because it's more cloudy out here, we don't know the exact boundaries. We have to be creative. So say we had an O2 molecule, which is the combination of two identical oxygen atoms. What they do is they can pinpoint the nucleus, so they measure from one nucleus to the other nucleus of that molecule and divide it in half, and that's how they determine the atomic radius. So again, when we're talking about radius, just think of the size of the atom essentially. Now what you might expect is, as I increase the atomic number, you might expect the size of the atom to increase because I'm getting more and more protons. However, what actually happens is we find that they become smaller as we go across the period. And this is because the nucleus gains a more positive charge. So you have those electrons, they're being pulled in stronger. So you have more nuclear charge bringing in the electrons and then making the atom smaller. On the other hand, as I go down a group, so as I go down the periodic table, I'm going to find that the atoms become larger because now I'm literally adding more and more energy levels. So you have the nucleus in the middle, your first energy level, the first period of the periodic table is going to be a certain size, and then once I add that second energy level, third energy level on, etc., I'm going to find that the atom gets bigger and bigger as I add more energy levels onto it. So to summarize, as I go left to right, the atomic radius decreases, but as I go from top to bottom, the atomic radius increases. I'm going to show you here so you can see. Whoops. So if we look at the atomic size, there's plenty of images out there that show this, kind of like this one. So this sort of shows me what you notice as I go left to right, starting with lithium, for instance, and going over to neon. I'm seeing the atom get smaller. Same with the bottom row. I see the atom get smaller as I go left to right. If I stuck these two, the F block, in where it belongs, you can kind of follow that trend as I go from like rubidium to strontium to yttrium, and then all the way across here. You can see that the atoms do get smaller as I go across all the way to xenon. On the other hand, as I start at the top and go down, you can tell that those atoms are getting bigger as I go down the row. One way I think it might be helpful to think about this is, which by the way, that some of these elements, not all the elements in the table are on here. I was mistakenly putting that 57 with yttrium. Really, it belongs in the bottom row here. But what I notice here is cesium, it tends to be the largest atom on the table, and helium tends to be the smallest that we have data for. So when you're comparing elements, think the general trend is as I go up and to the right, it gets smaller. So if I'm looking at, for instance, copper versus zinc, zinc is to the right, so zinc is smaller. If I'm looking at copper versus silver, copper is above silver, so it's smaller. So keep that in mind as we look at our trends in general. So as you can see, I have a general trend here. My picture got a little messed up, so it's on your notes it's not showing that where it decreases. But you can see if you want to draw arrows on your periodic table to help you remember that, the atomic radius is going to increase as we go from top to bottom, and then it decreases as we go left to right. So our sample problem here, we're comparing 4 elements. We're comparing magnesium, chlorine, sodium, and phosphorus. So if we look at magnesium, chlorine, so magnesium, chlorine, sodium, and phosphorus, which of those 4 elements would you expect to be the biggest? So again, it was magnesium, chlorine, sodium, phosphorus. So chlorine is actually going to be the smallest based on our thing. If we cheat and look at the sizes here, remember the size decreases from left to right. So yeah, it's going to be sodium. Good guess though. You'd think the higher, the more atomic number. It's for left to right it's opposite. However, realize as we're going top to bottom, it is as you would expect that way. But left to right, it's a little different. And again, the reasoning behind that is because you have a stronger nuclear charge pulling in the electrons. So the other thing we're going to talk about today is ionization energy. We're going to define ions. An ion is a pretty big deal in chemistry. You might have learned about ions in bio. But basically an ion is a group of bonded atoms or just an atom itself that has a positive or a negative charge. So an example would be sodium, and that should be a superscript there, that plus for the charge. Should be sodium plus whenever sodium loses an electron. And sodium loses that relatively easily. We just talked about sodium. Sodium's actually going to give that electron up pretty easily. And that process where an ion is made when an atom gives up an electron, bless you, that is called ionization. So we put an energy to it. How much energy does it take to remove one electron? So how much does it cost? You go up to an atom, you ask how much does it cost for your electron, and the lower energy or the lower price is the lower cost for that to take that electron. A higher energy would be, it's going to take a lot more to get that electron from that atom. So how does ionization energy trend on the periodic table? Typically in the main group elements, we're going to see an increase across the period. So literally the opposite of size, because what's happening is that increase in nuclear charge not only brings the electrons closer to make the atom smaller, but it also brings the electrons closer in order to make it more difficult to remove an electron. So again, higher charge is going to strongly attract those electrons. On the other hand, just the opposite of size as well, we're going to see those ionization energies decrease down the groups. So let me pull up my periodic table. and show you. We can actually look at P table. They tell us the ionization energy right here. Notice that the green color is the minimum and the blue color is a maximum. So you can see that trend, just the opposite of size, like how helium is very dark blue up here in the corner, and francium is a green, meaning francium has a lower ionization energy. Helium has a larger. It's going to be a lot harder to take helium's electrons away. And we can actually put numbers to that. You look at helium, it's 2,372, whereas francium is only 380. Again, that's how much energy it takes to remove an electron. So the analogy I always use, it's kind of a dumb analogy, but let's say you're dog sitting and you're trying to keep track of all your dogs that you're watching. If you are up here in the top row, so think your energy levels, how many energy levels your atom has. If you're up here in the top row and you only have to worry, for instance, say hydrogen's got one dog to watch, and then there's the town's got a dog snatcher going around. Going to be kind of hard to take that one dog from you, right? But francium down here, francium's watching 87 dogs. How easy do you think that dog snatcher would have to take a dog from francium versus take a dog from hydrogen? He's watching one versus watching 87. Who's going to have the harder time holding on to all their dogs? Probably francium, right? So I know electrons and dogs, two different things, but that's just how my brain works. So hopefully that helps you see, down here it's almost like I don't want to say they don't care, but it's harder to watch the electrons it's harder to keep hold of the electrons on the outside of their energy levels versus hydrogen, which only has one. And there's actually a literal term for that. It's called electron shielding. There's an effect that all the inside energy levels keep the nucleus from holding on to that electron as strongly as it could. So, again, the reason it does increase as we go across, we're not changing energy levels as we go from potassium to krypton, for instance. Krypton just has the same energy level, but more. It's almost like now there's more people helping you watch the dogs with krypton. So you have more people taking care of the dogs without much of an increase of the number of dogs. They're going to be able to hold on to them more tightly. And if it helps, again, just remember helium's got the highest ionization energy, francium over here with the lowest, and then we can compare elements in between. We do have a question, I believe, coming up here. Well, first, I guess I want to show you the graph. As you can see, and you're going to do this in your lab, as I move left to right, that ionization energy increases, and then every time I hit a new row, every time I get to the noble gas, it takes a sharp dive, and then it increases again, takes a sharp dive, increases again. Never really comes back up to where it was originally, but it keeps taking a dive, increases, takes a dive, increases. That's a periodic trend. It happens over and over and over again. That's what our periodic table looks like for each period. So here's my question. Looking at two main group elements, A and B, let's just say one is in the S block and one is in the P block. Do you think the 419, so you've got 419 kilojoules per mole, meaning it takes 419 kilojoules to remove an electron from a mole of that atom versus 1,000. Which one do you think would be more likely to be in the S block, and which one do you think would be more likely to be in the P block? Do you think the lower one would be over here in the S block, Or would the lower one be the P block? Well, at least you think so. Do you agree? Well, let's take a look, because we can actually look at the numbers here. So remember, I said francium's the lowest with like 380. So we see how there's like some 400s over here. This is my S block. Whereas the thousands, we start to see the thousands somewhere in this area in the P block. So the lower ionization energy happens on the left side on the S block. The higher ionization energy happens over there on the P block.
But if they're smaller over here, then bigger over here, wouldn't that make sense?
So smaller over here?
Yeah, that was the logic I was going off of.
So you're thinking they have smaller size. So the ionization energy is how much energy it takes to take an electron away. So because they're holding on to those electrons tighter, that's why they're smaller. It's also going to take more energy to remove the electron. Does that make sense? So I think you have the right logic. You just, as far as the energy needed to remove the electron, it's going to be higher because they're smaller. If that makes sense. So that's why I say, remember ionization energy, literally the opposite trends of the size. So they also ask us which is more likely to form a positive ion. So let's see if we can use logic to figure this out here. We've got one with like 1,000. Looks like sulfur's pretty close. Do you think it'd be easier to remove sulfur's electron or somewhere with 400 like who's got 400? Like rubidium. Do you think it'd be easier to remove rubidium, who's got 400, or sulfur, who's got 1,000? It takes 1,000. Think of it in terms of cost. It takes 1,000 joules to remove sulfur's electron. It takes 400 joules to remove rubidium. Whose would be easier to remove? It would be rubidium. It'd be like just if rubidium, my electron's going to cost $400. Sulfur's like mine's going to cost $1,000. Then it's going to be easier to take rubidium's electron. Rubidium actually wants to give it away for cheap. Rubidium wants to become a positive ion, so it essentially gives its electron away. Sulfur would prefer to become a negative ion, so it's going to hold on to its electron. Meaning that if I have more electrons, it's going to become a negative ion. If I lose an electron, that's how I become a positive ion. So you got to think, if I lose an electron, I'm becoming positive. So in that case, in other words, the one with 419 kilojoules per mole would be more likely to form a positive ion. So I just have one more question, and then we'll kind of cut it off there for today to talk about the rest tomorrow. But what do you think? As we move from left to right across the period from magnesium to chlorine, the energy needed to remove an atom, does it increase, decrease, or really not change at all?